So whenever a question has been asked from this particular section, it always comes from the examples. Okay, so you need to remember the examples with these basic mechanisms, either acid-base, metal ion catalysis, or covalent catalysis. So first of all, we were discussing covalent catalysis. So covalent catalysis is something, a process of covalent catalysis involves the formation of reversible covalent bond. Means obviously it is covalent catalysis. So a covalent bond must form between the catalyst, that is the enzyme, and the substrate. And this is a kind of reversible covalent bond. So when the reaction is over, so covalent bond will be broken and the product will be released, and the enzyme, there is no change in the enzyme at all. So it will reform, means regain its original shape. And conformation. So although the covalent interactions are temporary, obviously they are reversible, so they are temporary. They only occur for some period of time, but there are some very important examples in this particular section. So here are both are possible, either electrophilic kind of catalysis or electrophilic or nucleophilic kind of catalysis is possible. So if this is happening, so the two groups, one is nucleophilic, another is electrophilic. So nucleophile is anything which is having a negative charge. So obviously some of the amines, mean some amino acid groups which are having R group negatively charged, for example, carboxyl, hydroxyl, imidazole. Okay, so they are having free electron pairs. So, and thiol group, obviously it is having sulfur, so it is electronegative. So they are all nucleophilic centers. So they can work like nucleophiles, or nucleophilic, they can involve in the nucleophilic catalysis under the same category called covalent catalysis. Again, there are some groups these are R groups over some amino acids, for example, which are having positive charge. So electrophilic centers are mostly the phosphoryl groups, because phosphorus is positively charged. It is the electron density will be drawn with the help of oxygen atoms. So phosphate will have a positive charge. Acyl groups or some glycosyl groups, these type of groups. And for example, in modified proteins, the glycosyl groups may be present. This is a kind of post-translational modification in protein. So they are all working like electrophilic centers. So they will take part in the electrophilic covalent catalysis. So these two types actually. So now what type of examples we have discussed in this? So mostly in this section we have discussed proteolytic enzyme chymotrypsin actually, which is having the excellent example of this mechanism. Now, how this chymotrypsin actually, so the two things we have discussed in the chymotrypsin, first of all, we have seen how this chymotrypsin is being produced, and then we have seen how this is going to catalyze the reaction. So both are important actually. So whenever a chymotrypsin is going to activated. So there are some inactivated form of these enzymes which are uh, present every time, but these are not active. They are inactive form. Therefore, they're called zymogen state, so that they cannot do their functions, because these are all proteolytic enzymes. So they should be stored in an inactive form or zymogen form. So chymotrypsinogen is the zymogen form of chymotrypsin. So first of all, whenever it is going trypsinization, this is trypsin is going to cleave it here. So this 15 and 16 amino acid, which are linked via amide bond, or you say peptide bond, it should be broken. So it will lead to formation of pi chymotrypsin, which is though active but not that much active. Finally, there are some more amino acids which should be released out of this pi chymotrypsin to get the fully active alpha chymotrypsin. So two amino acid, one is 14 and 15. So I also told you the trick in last class. So to remember all this, you need to remember few things. For example, this can be remembered by, this is S, serine, this is arginine, R, this is threonine, T, and this is asparagine. You write asparagine as N. So if you write some letters in between them, so it is easy to remember these. So you can write star 10. So you can write STAR. Obviously, this T is here also. And this is the trick. Fine. So amino acids, two amino acids from here, 14 and 15 number, and from here 147 and 148. So you see there is gap, and these gaps or these chains A, B, C, there are three chains. So sometimes this question may be asked directly: how many chains are there in the active chymotrypsin alpha? So there are three chains A, B, and C. They are linked by disulfide bridges. So if you count, there are 5 disulfide bridges. So obviously there are 10 cysteine residue which are forming these disulfide bonds. So these amino acids are removed, and the amino acids which are left in these gaps, these are called liga. So this is leucine, this is isoleucine, this is tyrosine is Y, and alanine is A. So you can also remember the names of these amino acids which are left after removal of these S, R, T, and from these gaps, and these are called. Then we have discussed how, sorry, actually I need to remove all this. Okay. Also, we have discussed how this chymotrypsin is going to catalyze a reaction. So this chymotrypsin is having some mechanism. These are called serine proteases, and the serine proteases are a category of our family of enzymes, including chymotrypsin. There are others also: trypsin, elastase, thrombin, subtilisin, acetylcholinesterase, and there are other related enzymes are also coming in this class, but these are very famous. Okay, so you need to remember these are all serine proteases. Whenever we are talking about serine proteases, there are three amino acids which are present at the active site of the enzyme. You know the active site of the enzyme. Till now you are aware of the active site of the enzyme, where the site or the cavity over the enzyme where the substrate binds specifically to the enzyme, and actually where the reaction is actually happening is called the active site of that particular enzyme. I also told you enzymes are very much increasing the rate of reaction, because in evolution they are designed in such a way that the amino acids which are involved in the reactions are very close to each other. Means for example, see here, there are three amino acids in the serine proteases. So obviously it is serine protease, so serine should be there. It is working like a nucleophile. Okay, so it is having some negative charge. So serine 195 is actually the main amino acid which is catalyzing this particular reaction. Along with serine, it is having histidine and aspartate. Now see, they are very close proximity over the active site of the enzyme, if you see, but they are actually distant amino acids. So this is 195, this is 57, this is 102, but actually they are forming a charge relay system. So these are linked by some hydrogen bond, these are linked by some hydrogen bond. So you can see there are electron transfers can happen between these amino acids. Therefore, one kind of charge relay system, or this is called catalytic triad, actually formed, which is taking part in catalyzing the reaction in serine proteases. So whenever a serine proteases came into question as a question, so you should remember things. For example, this HSD is called catalytic triad here. So in serine proteases, including the chymotrypsin, trypsin, elastase, thrombin, subtilisin, acetylcholinesterase enzyme, these three amino acids are very important. So their number may vary from one enzyme to other, but the same family is having, for example, all the chymotrypsin proteins are having the same positions almost. Okay, but they may vary in the trypsin, elastase, and thrombin, for example. But they are the same category of amino acids. For example, histidine, serine, and aspartate D. HSD is called catalytic triad or charge relay system in these proteases. And the main inhibitor, actually, many times this question has been asked. So the diisopropyl phosphofluoridate, that is DIPF, actually. So this will inactivate the enzyme irreversibly. So once it is, because it will bind with this particular serine, and you know this serine is very important to this particular enzyme to catalyze a reaction. So if it will bind irreversibly with the serine and react with this and present in the active site of the enzyme, so this chemical modifications that usually reactive serine residue plays central. So this thing also shows that the serine is very important to this particular enzyme or this particular class of enzymes. Okay, so these things you need to remember from this covalent catalysis. Then we have discussed the other thing. So we have also discussed in the same category called lysozyme. So, okay, so I'm coming to lysozyme also. So here you will see, wait a minute. Okay, so we are having lysozyme here. So in lysozyme also we have seen that but these are having different category of amino acids. Here in one aspartate and one glutamate are very important in this lysozyme. And I also told you that this EC number is also important because sometimes the question may be asked like this particular EC number represent which of the following enzymes. So this is lysozyme 32117. I told you in the first class or the second class when we were discussing the classification of enzymes, this is called the main class. So this is obviously hydrolases. This is subclass and this is subclass, and this is a serial number of that particular enzyme in the order it was added to this particular class or subclass. Okay. So after this, memorizing this particular number, which is present in the secretions. Now, where this lysozyme is found, it is present in our tears, our sweat. It's also found in the egg white of the eggs, and this was discovered by Alexander Fleming. Then its structure was elucidated by Phillips in 1965. It was a monomer, so you should also know that what is the function. So lysozyme is responsible for cleavage of this particular bond. This question has been asked several times in many competitive examinations, including the university examinations, or I have seen this particular question in the CSIR or some ICMR examination also. Okay, so this beta 1,4 glycosidic bond, so you need to remember two things now. So whenever you are talking about structures, for example, cell wall or, okay, so these structures are mainly made up of beta linkages. So here there are two sugar units which are linked by beta 1,4 glycosidic linkage. Now, generally alpha is responsible for providing us the energy, for example, starch, glycogen. These are all alpha polymers, whereas the structural polymers or structural carbohydrate are having mostly the beta glycosidic bonds. So this is the first thing you will remember from this discussion. And the second thing is the two type of sugar residues which are present in the peptidoglycan of the peptidoglycan is present actually in the gram negative also, but in little amount. So generally the bacteria is having gram, can be divided into gram positive, gram negative, both are having peptidoglycan. Gram positive is having major peptidoglycan. So this peptidoglycan is made up of these two structures. One is called NAM, N-acetylmuramic acid, and one is called as NAG, so the N-acetylglucosamine. These are linked by beta 1,4 glycosidic bond. So this particular enzyme is going to break this particular linkage. I also told you that in archaea, this peptidoglycan layer is not present. Instead of beta 1,4, there actually the 1,3 linkage is present. So therefore, this lysozyme is not going to cleave the archaeal cell wall. But in bacteria or eubacteria more correctly, it will break between NAM and NAD, and this will lead to the breakage of this polypeptide. So this is polysaccharide actually, polysaccharide chain in the cell wall, due to which this cell will undergoing some hydrolysis. Okay, so cell will swell and rupture. So this will happen. Now we will learn, we have learned actually this glutamate and aspartate. These are two very important amino acid in this lysozyme chain, which are going to cleave the bacterial cell wall, or you say peptidoglycan. So suppose this is NAM and this is NAG, N-acetylmuramic acid and acetylglucosamine. Several other sugars are repeating in the same sequence. So it is going to cleave between NAM and NAG. So you also need to remember the sequence. NAM will come first. Okay. So first of all, this glutamate. Glutamate is, so suppose this is the enzyme active site, and here there is a residue called glutamate. This glutamate is having an R group. So obviously, you know, glutamate and aspartate both are acidic amino acids. So they will have COOH group. Okay, so glutamate will have two CS2, CS2, COOH, whereas this is having CS2, COOH. Okay, this is aspartate 52. Uh, Now these numbers are also very important because these specific amino acids are going to catalyze the reaction. So therefore they are becoming, so you need to remember these also. So first of all, this will provide this with this hydrogen, so that this hydrogen will go and bind here. Then a water molecule, this is water molecule coming from outside. This water molecule will come and it will give its, will be hydrolyzed. Hydrogen will be given back to the glutamate, and OH group will be. So this bond is already broken with the help of glutamate 35. Then a water molecule will come and compensate for the losses. So it will recover this particular hydrogen, will be given to the glutamate, so that it will come into its original state. And this OH group will be, so it will make a covalent bond with this aspartate. So to remove the product from the active site of the enzyme, and to get the enzyme in the previous state, this bond should be broken. So once this OH will be provided to this particular carbon, the valency of carbon will be completed, and that's how this OH will bind here. This CH will come here, and this aspartate and NAM bond, covalent bond, will be broken. So this kind of reversible covalent bond or catalysis can be seen in case of, finally, this is the enzyme, and the product, that is the lysed peptidoglycan wall, or the polymer polysaccharide, is released, and the enzyme will regain its original conformation. So that's how we have discussed two enzymes. One is lysozyme, one is chymotrypsin. We also have discussed one enzyme that is called RNase A in our discussion, if you remember from the last class. So this actually we have discussed in the section which is called acid-base catalysis. So first of all, I will tell you about acid-base catalysis, then I will tell you something about RNase A. Okay, so actually we have discussed this, but actually sir told me that one or two new students in this particular class, I don't know what they actually are. What? Priyanshi, Neetu, Ankita, Anshul, Shukla. Anshul is new student. I think Star, you were there in the previous class also. No problem, we can discuss this because these are important, so we cannot leave them as such. So it will take hardly 5 more minutes. So let's discuss acid-base catalysis. So this is the second type here given, and the best example out of this. So obviously this is acid-base catalysis, so involves some kind of proton transfer. So some H positive ions will be transferred from one to other. And we will see how actually exactly they are actually transferred. Now this can be divided into two main types. One is called as specific, one is called general. I highlighted the general because most of the enzymes are coming under this class. So, okay. So if it is specific acid-base catalysis, so specific because only hydronium ions and hydroxide ion, you know hydronium ions, H positive, H3O positive, like, and OH negative, these are hydroxide ions. So if they take part in the catalysis, so this is called specific acid-base catalysis. Now, what you need to remember about the specific acid-base catalysis, it is determined by the pH and there is no effect of the buffer concentration because these are H positive and OH negative ions are going to catalyze the reaction. But the other type is general, in which obviously there are no hydronium and hydroxide ions are going to catalyze the reaction. There are some other proton donors and acceptors. Now, from where these proton donors and acceptors are coming in the catalyzing the reaction, for catalyzing the reaction. So these are actually coming from the protein R groups or some cofactors which are interacting with the enzyme itself. So mostly the ionizable R groups are taking part in this particular catalysis. This is called general because there is no hydronium ion, there is no hydroxide ions. Obviously, if this is an ionizable R group, so it is going to affect by the buffer concentration. So mostly in the enzyme catalyzed reactions, we will see this general acid-base catalysis. Okay, so lysozyme is actually the example of this general class. Okay, sorry, actually I discussed that in the covalent catalysis. Okay, so then buffer affect the rate of overall reaction. So this is the main difference between the specific and general class. Here, buffer is having no effect over the enzyme catalysis, but here in the general category, in the general acid-base catalysis, buffer is going to affect the overall rate of the reaction. So now we will see, okay. So, okay. And everything is given same actually whatever we have discussed in the. So in general acid-base catalysis, donors and acceptors of the protons and other than hydronium ions and hydroxide ions, this we have discussed. In such cases, the ionizable functional groups of the amino acyl side chains and of cofactors present contribute to the catalysis by acting as either as acids or bases. Okay, so we will see actually how this is going to affect. So in case of lysozyme, okay, this is given. Okay. Sorry. So here actually we will discuss this again. This is lysozyme, and in this there are two groups. So you will see here this is going to donate this particular proton H positive ion to this. So this will work as, so it is actually donating the proton to the bond, glycosidic bond to the sugar, and therefore it is acting like an acid. Okay, so proton donor is acid, acceptor is a base. So here it is acting, so glutamate 35 is an acid, here it is a base. So this is forming a covalent bond then, and therefore so actually you can categorize this in both types. Actually the covalent bond is also formed, the acid-base catalysis is also happening. And actually this I forgot to tell you the most of the enzymes actually. So actually this is written also. So see here. So most of the enzymes, so it is also possible. For example, we had discussed lysozyme, for example. So a combination of several catalytic strategies. So they're talking about three basic types: acid base, metal ion, and covalent catalysis. So a combination of several catalytic strategies is usually employed by an enzyme. It is also possible that an enzyme may employ either a combination of these catalytic strategies. So you have seen that covalent bond is also formed, so you can categorize that as a covalent catalysis. But this is also coming under the acid-base catalysis. So if you want to discuss a pure example of acid-base catalysis, so you will go, for example, this chymotrypsin also, for example, it is also a good example of which is using both the covalent catalysis and acid-base catalysis. This also is the same example, but if you want to discuss a pure example of this acid-base catalysis, so it is actually given in the void. So this one actually, this is RNase A. Why RNase A? Because it is going to degrade the RNA. You know RNA? RNA is a polymer of ribonucleotide. So the RNA, the sugar is called ribose, whereas in DNA it is deoxyribose. So what is the major difference between an RNA and DNA is over this 2 prime. So this may be a basic question. So this should be in your knowledge. Whenever we are talking about RNA, so it will have a OH group over this 2 prime carbon of this ribose sugar. This is called ribose sugar because it is having OH. If it was DNA, it will not have this hydrogen. So it will not have the oxygen. Deoxy means the oxygen will be removed and it will only have the hydrogen. Okay, so and this is a disadvantage for RNA because it is having a functional group or reactive group here. Therefore, it may undergo the catalysis or breakage. So it is very susceptible to, and it is very unstable. Therefore, so actually, how this RNA is going to degrade the RNA? Now we will discuss. There are 2 amino acids. So suppose this is an enzyme, this brown color enzyme, and as we discussed that in evolution, for example, this is 12 number histidine and this is 119 number histidine. They come very close. They come in very close proximity. So the enzyme was designed in such a way in evolution that both are important in the catalysis. Therefore, they come very close to each other. Now they will work as in the acid-base catalysis, and there is no covalent bond formation here. So first of all, what will happen? This lone pair of electron will be donated to this one. So in first reaction, this will, oh, sorry, it is going to accept this one. So this is more clearly given in your Pathfinder itself. So we will discuss this from here. I know these are little complex, but if you read them 1 or 2 times, I believe you will learn actually what we are discussing here. So this is ribonuclease A, RNase A given in your Pathfinder. So ribonuclease, or actually this is almost the end of first chapter. So if you look for some pages at the last of first chapter part 1, you will get these enzymes. So RNase A is a ribonuclease, or RNA is a group of enzymes in which many different types of enzymes are coming, which are going to degrade the RNA in some ways. But this was isolated from the bovine pancreas. So this bovine pancreatic ribonuclease A, we know most about this particular enzyme because we have studied this RNAs in more details. So it is going to catalyze the hydrolysis of phosphodiester bond in single-stranded RNA between the phosphate group of the pyrimidine nucleotide. You know pyrimidine, these are one either C, U, or T. Okay, and there are 2 purines, either A or G, and an adjacent nucleotide to give a 3' phosphate and an RNA fragment on 5' terminus. So in first reaction, so first of all, this particular 12th number histidine is going to donate this lone pair. So, or it will accept this particular proton. Okay, so this H positive will come here and will, so this will going to accept, so it will work like a base. It is going to accept this particular hydrogen. Once this hydrogen will come here, this will develop a negative charge. So this will become alkoxide. So this is important. Alkoxide anion, that is a nucleophile because it is having a negative charge, then attack the positively charged phosphate, because you know this phosphate is surrounded by 4 different oxygen atoms. So they are all having negative charge, electronegativity. So it will have develop a del positive charge. Therefore, this will attack here and will break this particular bond. So it will form something like this. So this cyclic form, or this is called 2', 3', rest we will discuss from the void actually. So suppose this will attack here and this will lead to the formation of this kind of complex. This is called 2' 3' cyclic nucleotide intermediate. Then a water molecule will come and resolve the issues. So this water molecule, this is green color. So the green color atoms will be given. So first of all, this particular, so this is the last step, second step. In the second step, so in the first step, the 12th number histidine is going to act like a base, and this will work like an acid. In the second step, it is reversed. So this will work like a base and this will work like an acid in the second step. So suppose this is a water molecule. So OH will be donated to this bond so that this will, this cyclic intermediate is broken. And the actual enzyme, which is having histidine 12 and 119, are restored back, and eventually these products are released out of the active site of the enzyme. Then we will move to another kind of catalysis that is called, so this we have discussed, now we are coming here. Okay, so most important, the third one, which we are starting today, whatever we have discussed up to here, actually we also have discussed in our previous class. So metal ion catalysis, this is important. So metal ion catalysis is also called Lewis acid base catalysis because there are some enzymes which are catalyzing the reactions depending upon the metal ions which are present in these particular enzymes. So these metal ions can be of two types, means they are interacting with the enzyme in two ways. Either they are tightly bound, tightly interacting with the enzyme, therefore these enzymes are called metalloenzymes. Or there are other category of enzymes, these are called metal activated enzymes. So it is possible that metal ions are only activating the enzyme or metal ions are part of enzyme itself. Okay, so the ways, in two ways also it can catalyze the reaction. First of all, electrophilic catalyst. This is stabilizing the increased electron density and negative charges over the reaction intermediate. So the word stabilizing is very important because most of the times these ions are going to stabilize the charge or the electronegativity or the negative charge over the reaction intermediate or the substrate, as you have seen in case of kinases. If you know kinases, in most of the kinases actually, so I will show you here. So if there is a metal ion, so suppose this is a metal ion. So actually this is this another example. So this is given here, metal ions promote the catalysis through the charge stabilization. Now what is charge stabilization actually? So one example is given here, but actually I'm going to discuss something else. Okay, so this is charge shielding actually. So, okay, so here, for example, suppose there are some kinases. Kinases are the class of enzymes which will require or utilize ATP to catalyze a reaction. So what will happen actually, this ATP, which is made up of adenine, a ribose sugar, and alpha beta gamma phosphate, a magnesium ion or manganese ion is generally required if you know about the glycolytic reactions, glycolysis reactions. So the kinase will also utilize either magnesium ion or manganese ion. Why this magnesium ion is required? So you can better see here, because this ATP is having a more negative charge over these two beta and gamma phosphates. So this gamma phosphate is going to be transferred from over the substrate. So this magnesium ion, which is Mg2 positive, is going to neutralize shielding this particular charge over this particular ATP. So that's how they are, these enzymes or kinases are needing these magnesium ions or other metal ions so that they can shield the charge of ATP, so that they are this gamma phosphate can be easily transferred to the substrate. Another example which is very famous, this carbonic anhydrase. You know carbonic anhydrase? Carbonic anhydrase is an enzyme which is required, which is present in RBCs. So with the help of water, it can convert carbon dioxide into H positive and HCO3 negative in an overall reaction. Okay, so it will require a zinc ion, you all know, because in the first class itself, I told you some of the enzymes are importantly required, these metal ions. So it will require the zinc ion. Now you will see these are three imidazoles. I am for imidazole. These three imidazole will come from the histidine residues. So this particular enzyme, carbonic anhydrase, will have three histidine, which will form a complex with this zinc ion. And this zinc ion will make a chelate with three water molecules. So suppose this is water molecule H2O, this is water molecule, this is water molecule. Now it is more clear from this particular discussion. So suppose there is a histidine 64 and this zinc ion is making a complex with three other histidine, and this ribbons, actually these ribbons are carbonic anhydrase chain, amino acid chain. So now you will see this histidine is very far from this particular zinc. Okay, so therefore three water molecules will come. These red color ions are actually the water molecules. So these water molecules will come and they will act like a proton shuttle. Okay, so they will act like shuttle so that this gap can be maintained, or this gap can become short. So this kind of proton shuttle has been seen in case of carbonic anhydrase. In one reaction, this one finally the last one, this particular water molecule will be hydrolyzed and will bind to this particular zinc, and this hydrogen will go and will bind to the histidine 64 imidazole ring. This is the histidine. So there are two possible conformation. One is called N, one is called out. Normally it is present in N conformation, but when this reaction will happen, it will conformation will change, and this is a cyclic way actually happening. So that's how then when this OH negative will bind with this zinc ion, why this zinc ion is very important for the catalysis of carbonic anhydrase. So this is having a negative charge, so it will work like a nucleophile, and this will attack, this is going to attack our CO2 molecule. So this is CO2. Okay, so this carbon is having a positive charge. Krishna is asking, not clear with the glutamate and aspartate catalytic reactions. Can you repeat once again? Are you asking for, Krishna, are you asking for lysozyme? Sorry, I did not see your query actually. So, yeah, okay. Okay, wait for a minute. Actually, I will finish this carbonic anhydrase and then I will again repeat that lysozyme. Okay, fine. Okay, I will tell how this is going to catalyze the reaction. No problem. So this is CO2. You know the carbonic anhydrase is going to convert the CO2 into HCO3 negative. Okay, so you know the reaction. So if you know the reaction, actually you know the half thing. Then you need to know the mechanism, how it is happening. So this is happening with the help of this zinc ion. So therefore this is called metal ion catalysis. So the three water molecules, out of which the last one is hydrolyzed and converted into the H positive and OH negative. H positive is donated to this histidine 64 imidazole ring here, and so this H will come here and OH will come here. So this OH will work like nucleophile. You know nucleophile, it will going to attack some positive charge species. So this CO2 is having two oxygen atoms which are very electronegative. So they are electronegative. So obviously a positive charge will be developed over this carbon. So this ion or this lone pair of electron is going to attack this carbon so that a bond will be formed. So this is called HCO3 negative will be formed. So in this reaction, the water molecule will, one more water molecule will come and it is replaced. It replaces this red colored OH negative so that other water molecule will be hydrolyzed and this will replace this. And finally, this HCO3 negative will be released out of the enzyme. So that's how the carbonic anhydrase is catalyzing an bidirectional reaction in which it is making HCO3 negative out of the CO2, because you know CO2 is less soluble in blood and this is more soluble, and this is the only way to remove the carbon dioxide from. Okay, so this is not the only way. Another form, in form of CO2 also, it is really removed out of the body, but SO3 negative is one way, you know, with the help of carbonic anhydrase enzyme. I think this is clear because this is not very complex. This is very simply shown here that how this is all happening, and these cartoons are very helpful in understanding the mechanism of this particular reaction, carbonic anhydrase and kinase reactions. So the second reaction is kinase. Actually, this is also shown here. So the two things you need to know, these metal ions are either going to shield the charge or either they are stabilizing the charge. Okay. So the third form was also reported, in which the metal ions have promoted the nucleophilic catalysis via the water ionization, as in the case of carbonic anhydrase. So these three possibilities are there. Now Tushla is having one query, so let me quickly revise this particular lysozyme because she's not able to understand how aspartate and glutamate are catalyzing the reaction. So actually this question has been, this lysozyme is important. Many questions can be directly asked, out of which one is someone can ask, what is the intermediate which is going to, which will form in this particular reaction? So in the previous class also I told you that this is given here. This is called carbonium ion. So you need to underline this carbonium ion intermediate. So this will form until it reacts with the free water molecule. Then a free water molecule will come in the reaction, and then finally this carbonium ion intermediate will be resolved. Okay, so first of all, see, this is your peptidoglycan cell wall of the bacteria, in which this species is, D species is called NAM, N-acetylmuramic acid, and this is called N-acetylglucosamine. Now this lysozyme is going to break this particular bond because it will always break between NAM and NAG. When the NAM is first, NAG is second. So NAM will come first always. Now suppose this is an enzyme, lysozyme, which will have two amino acids, which one is glutamate, other is aspartate. First of all, this glutamate is going to donate. So this will work like an acid, this H positive to this glycosidic bond. So this is a glycosidic bond, beta-1,4 glycosidic bond between these two residues. Once this H positive is going to will be donated here, this bond will be broken in this particular step only. But okay, so it will be broken here. So this OH will here, and this D residue will make a covalent bond with aspartate 52. Therefore, both glutamate and aspartate are important, because in the first step, if this glutamate will not donate its H positive or hydrogen ion or proton, this cannot, this is glycosidic bond cannot be broken. And aspartate is important because it is directly making a covalent bond with the D residue or the NAM residue of the peptidoglycan. So it will hold this D residue or the remaining, because there are a chain. There is a complete chain. If you will see, there are lots of other sugar residues also. So it will hold this particular thing in place. Therefore, this aspartate is also important. Then there is an entry of one water molecule. If you are able to see this HOH, this is a water molecule, and this entry of this water molecule will resolve this carbonium ion. Okay, so this will donate its proton to this to regain, you know, actually this was like this. So this H will come here. So the enzyme will regain its original conformation, and this OH will be donated here so that this covalent bond can be broken again. And these two, because this glycosidic bond is broken, Now this is product A, this is product B. This should be released out of the enzyme, and enzyme should regain its original conformation. So see here, this glutamate is as such, and aspartate will also regain the same conformation as as was in the initiation of the reaction. And these two products, this is also having a chain of sugars, this will also have a chain of sugars, but this glycosidic bond, beta 1,4 glycosidic bond, is broken, therefore it is released. So this arrow is showing that these two products are released out of the enzyme. Krishna, I think this is, when you will read this particular thing from this Pathfinder, you will able to get everything, because this is very correctly presented in this book. Fine, very good. Then we have discussed actually all the three ways of catalysis. And one more thing, actually, I forgot to tell you in this. Actually, this third one, we have discussed covalent catalysis, we have discussed acid-base catalysis, we have discussed metal-ion catalysis also. Metal-ion catalysis involved some of the enzymes, for example, kinases, for example, carbonic anhydrase. So the electrophilic catalyst, which is going to stabilize the electron density, for example, in case of kinases, or provide a powerful nucleophile at a neutral pH. This is also pH, and this is also possible. This powerful nucleophile at a neutral pH, for example, this is in the case of carbonic anhydrase we have discussed. So this powerful nucleophile is formed out of water molecule, which will directly bind in the form of OH negative to the zinc ion, which will be transferred to the CO2 actually to make HCO3 negative. Okay, so this third one, metal ion catalysis, or this is also called Lewis acid base catalysis, these represent about 1/3. So you need to remember here, these are counting for 1/3 of the enzymes are actually showing this metal ion catalysis. Then there are other forms are also reported in which they are called electrostatic catalysis, they are called proximity or orientation effects. And actually this was the hypothesis also, in which there are two things are happening. One is proximity, one is orientation. Means the enzyme will hold the two substrate molecules in such a way that they can collide with a resultant reaction, so that the reaction can happen actually. And also there is a thing, preferential binding of the transition state complex. So the transition state complex will bind to the enzyme more efficiency. So let's also look into these classes. But before that, there is an example of metal ion catalysis. So you will look here. So, this one is an example of an enzyme called luciferase. Okay, so actually this is called, the name of enzyme is ecurin, and actually this was purified from the jellyfish, and it is responsible for the luminescence in the jellyfish. If you are able to see this orange colored pinch out of this jellyfish, so this luminescence property is due to this particular ecurin molecule which is present. So the enzyme catalyzes the oxidation of a compound by oxygen in the presence of calcium ions to release the carbon dioxide, and light is emitted so that this is glowing actually. So exact reaction is actually happening in the presence of calcium ions. So therefore this is an example of metal ion catalysis. So suppose this is an enzyme, this is a substrate, this enzyme ecurin is going to oxidize it with the help of oxygen and some metal ions, so that this will be converted into this form, and this process leads to the release of carbon dioxide, and this light is emitted, which is having some wavelength 466 nanometer, which is having some orange, yellow orange color. Okay, so therefore this is Then there is a line. Metal ions are often much more effective catalysts than the protons. Okay, so we have discussed acid-base catalysis, then we have discussed metal ion catalysis. So these metal ions are better than acid-base catalysis alone because in most of the cases, these metals are having, for example, magnesium ions, Mg2 positive, manganese ions, cobalt is having 3 positive charges, iron is having Fe2 positive or Fe3 positive. So in this way, metals may have more than one positive charge, whereas the protons are having only one positive charge. Protons, because metal ions can be present in high concentrations at a neutral pH and can have the charge greater than +1. Therefore, these metal ions therefore called superacids. Okay, so sometimes they're called superacids also because they're having more charge over the same metal ion. So this we have discussed. Actually, this is carbonic anhydrase, which is catalyzing this particular reaction CO2 plus H2O to convert them into SO3 negative and H positive. Uh, This zinc ion is very important, and actually it is present at almost 15 angstrom. You know, angstrom is 10 to the power minus 10 meter deep active site cleft. So it is always present there, and there is a evolutionary conserved 3 histidine residues which are responsible for binding with this zinc ion actually, and an oxygen atom of either end. This oxygen atom will come from the water or from the HCO3. So it is also given here. So it's coming from either from the HCO3 negative or generally from the water, H2O. And mostly this is present in conformation, and it is making an H positive or proton channel. So you see, this is a proton channel because they're present far distant from each other, histidine 64 and the zinc ion. Therefore, these water molecules, 3 water molecules are required for the catalysis to happen. Then this OH negative ion, which is bound to the zinc, nucleophilically attack the nearby enzymatically bound CO2 and convert it into the SO3 negative. This we have discussed. So the other category is also the charge shielding. Also, the metal ions are also involved in charge shielding. For example, in kinases, this is ATP molecule, and ATP, the charge is shielded with the help of some magnesium ions, Mg2 positive ions. If so what may be the consequence if these charges are not shielded? So otherwise, these charges would tend to repel the electron pairs of attacking nucleophiles. So the 2 nucleophiles will come close to each other, and these are all having negative charges. Therefore, they will repel each other and thus interfere with the reaction. Now we are having the 4th class of category of catalysis. This is called electrostatic catalysis. So this is not so much important, but actually I want you to go through it. At least you are able to understand what is happening in electrostatic catalysis and proximity and orientation catalysis. So the binding of the substrate generally exclude water from the enzyme active site. You need to understand the few lines in this electrostatic catalysis before you are able to understand what is actually happening. So suppose there is a substrate. When the substrate will bind to the enzyme active site, it will replace already present water from the active site. Okay, so some water molecules are already present at the active site, but once the substrate will bind to the active site, it will lead to the release of these water molecules, exclude the water from there. So if these water molecules are removed from the active site, so there is obviously a change in the dielectric constant. So electrostatic catalysis is directly correlated to the dielectric constant at the active site. So now if you understand the organic solvent, so water is a polar molecule, and best example if I give you for an organic solvent, this can be a zinc, for example. Sorry, this can be a benzene, for example. So benzene and water both are having different dielectric constant. Benzene is having less dielectric constant. Water is having 78.5, that is almost 80 value of dielectric constant. So this electrostatic interactions are much stronger than they are in the aqueous solution. So what will happen? So the electrostatic interactions are inversely correlated to if they're in the aqueous solutions, because in aqueous solution the dielectric constant is very high. Therefore, the electrostatic interactions are much stronger. Oh, sorry, much less in aqueous solution. Whereas in organic solvent, these electrostatic interactions are much stronger because the dielectric constants are less. So if you are able to understand this now, this is very understandable. The charge distribution on a medium of low dielectric constant, for example, an organic solvent, therefore can greatly influence the chemical reactivity because they will influence, they were having the electrostatic interactions are much, much stronger in the organic solvents, okay, or in the low dielectric constant. Therefore, and we also know this, the in amino acids, the pK value, pK value is, or the pK value जो भी है, are very important in proteins, which may vary by several units from their nominal values. Okay, so because of the proximity of the charged groups, because these pK values of amino acid side groups are affected because of the proximity of the charge groups about them. So there are mounting indications that the charge distribution about the active site of the enzyme are arranged so as to stabilize the transition state of the catalyzed reactions. Charge distributions about the active site. So there are some amino acids which are present at the active site, which are having the pK value or these side groups of the enzyme. So they are arranged in such a way so that the transition state can be stabilized in the catalyzed reactions. So if you compare them, so this resembles the form of metal ion catalysis that is discussed above. Therefore, it is something related to the metal ion catalysis, but actually there is no metal ions which are involved directly in these reactions. Instead, these are R groups which are having some charge which are involved in catalyzing the reaction. Therefore, they are called electrostatic catalysis. Okay, so this is the fourth type. Charge distribution apparently serves to guide the polar substrate. Now, what is the role of these charge distributions over the active site or the charge distribution? It will guide the polar substrate. For example, water is also a polar molecule, but it is talking in terms of some substrate which is going to bind at the active site of the enzyme, and enzyme is going to catalyze the reaction towards the binding site so that the rate of these enzymatic reactions are greater than their apparent diffusion control limits. So obviously, if these polar molecules or polar substances or substrates are guided towards the active site of the enzyme, the rate of enzymatic reactions are generally greater than if they are not present. Okay. Fine. Beside this electrostatic catalysis, the two theories are also important. One is called proximity, one is called orientation effect. So what is proximity? Proximity is to bring two things or the two substrate in close proximity or in close contact. But this orientation is going to affect the most of the reactions. Okay, so this is given over page number 513, Voigt and Voigt. And the two things are very important, proximity and orientation, though you are able to understand what is proximity, what is orientation effect. So orientation is a kind of effect when enzyme enable the substrate molecules to interact with one another in specific orientation so that they can react with high efficiency. Now the question is whether this, because we are talking in two terms, one is proximity, one is orientation. So the question is whether the proximity is going to affect the reaction maximally, or the orientation is going to affect the reaction uh, majorly. Okay, so there is query. Let me see first. Okay, so there is a query. What is the name of the substrate on which occurrence function? Okay, so the name is not given actually. So this is some chemical compound which so it is a normal substrate of this particular protein or this particular enzyme. So nobody is going to ask you this particular question. Okay, product. Oh, come on, you may find this one. Trishla, this is not given actually. So the thing which we have discussed in this particular section of Acurin, or this particular calcium mediated thing, obviously these are some chemical compounds. But what is important in this particular reaction is the light which is emitted as a result, due to which this jellyfish is okay, showing this luminescent property. You will find it out. Okay, no worries. Nobody is going to ask this one. What is the substrate? So we are discussing two important things. Okay, so whenever we are talking in terms of proximity and orientation, the question should come into our mind whether this proximity is having the major role, or the orientation is having by the catalyst is having the major role in catalyzing a reaction. So So the reactant must come together with the proper spatial relationship for a reaction to occur. Until and unless there is no proper spatial relationship between the two substrates, the reaction cannot happen and product will not be formed. Now there are 2 points. One is proximity alone. If you count for the proximity alone, it will contribute relatively little to the catalysis. So it will only little contribution. Okay, I will tell you how much. Uh, Actually, the orientation effect of the catalyst is the major one, which is going to catalyze the reaction. So properly orienting the reactants and arresting their relative motion until and unless the products are formed can result in large catalytic rate enhancement. So if someone asks you out of proximity and orientation, which is the major effector of the rate of reaction, so it is always the orientation effect of that particular catalyst. So it will orient the substrate in such a way that the reaction will occur at the maximal rate. Okay. So it is also given here, the molecules are not equally reactive in all the directions. This is very obvious because in all the directions, they are not going to react with each other. But they will react most readily if they have the proper relative orientation. So this is very important. If they are having a proper relative orientation with each other, the reaction can happen and the rate of reaction will be enhanced. So the approach of reacting atoms along the trajectory that drives as little as 10 to the power 0, and this is very less actually. So 10 to the power 0 is equal to 1. So if there is a trajectory or this much actually happen by a factor of 1 from this optimum direction, this can reduce the reaction rate as much as factor of 100 times. So if you move the substrate, so one thing he is talking about proper relative orientation. If you move the substrate from the proper relative orientation by a factor of 10 to the power 0 or by a factor of 1, it will reduce your rate of reaction by a factor of 100. So this is very important relation. Okay. So this is showing how important is the relative orientation of these two substrates so that a product can form and the reaction can happen. A molecule may be maximally reactive only when it assumes a conformation that aligns its various orbitals. So what is important? Why you need this proper relative orientation? Because the orbital in that particular conformation, it will align the various orbital in that particular substrate or compound in such a way that minimize the electronic energy of its transition state. This is important. We know, we also have discussed this one, that the energy of the transition state should be minimized so that the enzyme catalyzed reaction can happen at an enhanced rate. More number of substrate can be converted into the product. So if something is happening, that will minimize the electronic energy, and it will, various orbitals are aligned in such a way that this energy, electronic energy of the transition state is minimized. And effect, it will termed as stereo electronic assistance. So it will get some kind of assistance or help in stereo electronic control. Okay, so that will result in the enhanced reaction rate. Okay, so before discussing this from page number 513 void, there is a question. So we were discussing some of the enzymes with this enzyme commission number. So the first enzyme, which is having enzyme commission number 1111, is the alcohol dehydrogenase, which was extracted from the yeast actually. So this is yeast alcohol dehydrogenase. So because the scientists in the initial phase were studying or discovering the yeast alcohol fermentation, and this particular enzyme alcohol dehydrogenase is going to catalyze that particular reaction, converting the sugars into the alcohol. And therefore the systemic name of this particular enzyme is alcohol to NAD positive oxidoreductase, because in this reaction, this is a kind of oxidation reduction reaction which can also be detected from here because it is having a class number 1, and we know the class 1 is always oxidoreductase enzyme. Okay, so this is class oxidoreductase, this is the subclass, this is subclass, and this is the first enzyme discovered in this part. So enzyme commission, if you see this number, it is always alcohol dehydrogenase. And one more thing I want to tell you, alcohol dehydrogenase is also an enzyme. This is a metallo enzyme, and it will require the zinc ion for the catalysis of the reaction. This we have already discussed. Now we move to the page number 513. So here's the void. So 513. So electrostatic catalysis discuss a little bit, not very much details because this much is actually given in this book. Uh, there is proximity and orientation effect. So they have discussed many things about the proximity and orientation actually, because this is really important. And they have shown that if there is a 20-fold effectiveness in the rate of reaction, it is showing the enzyme is going to increase the concentration of the substrate 24 molar from 1 molar, means 24 times. So it is simply showing at the active site there are more number of substrates, so that the concentration of substrate is almost increased, therefore the rate of reaction is increased. This proximity is overall it is helping the reaction to happen, but overall what is important is actually the orientation effect. Okay, so they have discussed. So proximity and orientation effect. So obviously there are some orbitals for each atom. For example, carbon is having this tetrahedral arrangement of atoms, and there is some X group, there is some Y group, which are also having orbitals, electronic orbitals. So it is necessary that, so this is some intermediate which is formed between when the and reaction is happening in a way that AB is going to convert into the AB product. So these electronic clouds should interact with each other, and if they interact more efficiently, the reaction will be more efficient. Therefore, okay, so therefore, So in proximity, it freezes out the relative translational and rotational motions. So obviously, if you know about these type of motions in a molecule, there are always different type of motions which are actually happening. One is called translational motion, one is called rotational motions. So they will decrease the entropy. And what this proximity is to, what is the function of proximity to bring these two substrate or atom together so that their translational and rotational motions can be freezed, means can be removed, so thereby enhancing their reactivity. So similarly, the enzymes bind substrate in a manner that both align and immobilize. So there are two things are happening. One is orientation is actually the aligning. Immobilizing is actually the proximity them so as to optimize their reactivities. The free energy required to do so is derived from the specific binding of free energy of substrate to the enzyme. So we also discussed how this free energy is going, how this binding energy or the specific binding is helping to lower the activation energy of the substrate so that the reaction can be enhanced. Okay, so next is catalysis by preferential transition state binding. This we will discuss in next class. So if you're having some question from today's class, you may ask. I'm unmuting you all for some time.